Hello and welcome to our presentation. We are from the Applied Science Faculty AS120 from Group A4 AS12026. In this video, we are gonna explain you about the maximum and minimum problems. This is our group members that consists of 4 that going to present to you about the maximum and minimum problems.
Definition of maximum and minimum problem. Many application problems in calculus involve function for which you want to find maximum or minimum values. The restrictions stated or implied for such function will determine the domain from which you must work. The function together with its domain will suggest which technique is appropriate to use in determining a maximum or minimum value. For example, the extreme value theorem, the first derivative test, or the second derivative test. The first step for the maximum and minimum problem is, the first one is find the derivative. The next one is let the derivative equal to 0 and find the values of the variables. Next is second derivative test. If second derivative test more than 0, that means it's minimum. If second derivative less than 0, it's maximum.
Problem statement is a closed cylindrical container of radius r and a height h is covered with hemispherical lid of radius r as shown in figure below, given that the volume of the container is 45 pi. So, the first question is asking to express h in terms of r. So, in order for us to express the h, we need to know which formula are using the h. From the formula that was given, the only formula that are involving in using h is the formula of volume. Since the cylindrical container and hemispherical is one object, we need to combine both formula of volume. So then we will get the total volume of pi r square h plus 2 over 3 pi r square equal to 45 pi. Then we switch the place of pi r square with 45 pi. Thus, we will get pi r square h equal 45 pi minus 2 over 3 pi r square. Finally, we solve and supplement the equation and we will get h equal to 45 over r square minus 2 over 3r. For the next question, the question is asking to show that the total surface area of the container is S equal to 5 over 3 pi r square plus 90 pi over r. So, in order for us to solve this, we need to combine both the formula of surface area of cylindrical and hemisphere, which is we will get S equal to, in bracket, 2 pi r h plus pi r square close bracket plus 2 pi r square. And then we will substitute the h value that we get from the first question into the S equation, and we will get 2 pi r in bracket 45 over r square minus 2 over 3r close bracket plus pi r square plus 2 pi r square. And next we just have to multiply and plus the equation as normal, and in the end we will get S equal to 5 pi r square over 3 plus 90 pi r over r square. Lastly, we must not forget that we need to make sure that the equation that we get in the end must mark be as shown as in the slide.
For the equation 1c, in order to find the radius of cylinder, that is consists of 3 steps. First of all, we need to find the derivative for this surface area equation. So, from 5 pi r square over 3 plus 19 pi r over r square, we get 10 over 3 pi r minus 19 pi r power of negative 2. Next step, we need to let the derivative equal to 0. So 10 over 3 pi r minus 19 pi r power of -2 equal to 0. After that, we move negative 19 pi r, the power of -2, to the right side, and we get 10/3 pi r equal 19 pi over r square. And then we move power of 2 from the r to the left side, and we get 10/3 pi cube equal 19 pi. After that, we move 10/3 to the right, and we get r cube equal 19 pi over 10/3 pi. And then we simplify r cube equal 19 pi r over 10/3 pi. We get r cube equal 27. Lastly, we move the power of 3 to the right side, and we get r equal 3. Step 3. To find the maximum and minimum point, we need to find the second derivative test from the first derivative. So, from 10/3 pi plus 118 pi r power -3, we get 10/3 pi plus 118 pi over 3 cube. When r equal 3, substitute the r with 3, and then we solve the equation and get 31.42. The value r is more than 0. It means that is a minimum value. Next question 2a. To find total area, we must multiply x with y, and then total length equal 5x plus 2y. 2y equal 200 minus 5x. Move to right side, and we get y equal 200 minus 5x over 2. And then simplify. Y equal 100 minus 5x over 2. Total area A equal x multiply y. So we get A equal 100x 100x negative 5 over 2 x squared.
So, for the question B, which is determine the dimension of the field that will maximize the total area. First of all, we need to find the derivative. So, from the area equation, which is 100x minus 5 over 2x squared, we derive it to 100 minus 5x. After that, we let the derivative equal to 0. So, we get 100 minus 5x equals to 0. And then, we solve it using basic algebra until we get x equals 20. The next step is to find the maximum value. We need to find the second derivative test to find the maximum value. So, the first step is we need to derive the first derivative test to get the second derivative. So, we will get minus 5. The value we get is less than 0, which means that x equals 20 is a maximum value. Lastly, we let x minus 20 into the total length equation, which is 5x plus 2y equals to 200. Then we solve it and we get y equal 50 meter. For question C, we need to find the maximum total area. So we just need to multiply x and y, which is x is 20 and y is 50, and we get 100 meter square.